there is one presentation outline. The first one is introduction, material, method, characterization, result and discussion, and the last one is conclusion. Now we go to the first part, that is introduction. I believe that all of you already know what is nanomaterial. Nanomaterial is a particle that are composed of up to 10 of thousands of atoms, but confined to size less than 100 nanometers. Why we choose silver nanoparticles? Silver nanoparticles possess an interesting interaction with light due to the dielectric constant, which enable the occurrence of light with times in the visible regime. It also has great interest by the electronic, magnetic, thermoelectric, and optical properties in nanometer level. Due to their small size, silver nanoparticles have a large fraction in surface atoms, so that it has high surface to volume ratio. The high surface to volume ratio combined together with such effect with silver nanoparticles is quickly different from those of bulk material. In this study, we have two-step preparation of silver PMMA nanocomposite. The first one is chemical reduction method to synthesize silver nanoparticles, followed by the institute technique to synthesize silver PMMA nanocomposite. We choose chemical reduction method because it is simple and economical technique. It is also what is used to produce nanomaterials due to the straightforward nature and their potential to produce large quantities of the final product. While in the institute technique, silver nanoparticles can be generated inside of polymer by reduction of silver ion to zero-valent silver that are dispersed in polymer matrix. Below are the materials used to synthesize silver PMMA nanocomposite. For the synthesis of silver nanoparticles by chemical reduction method, I use silver nitride as a source of silver ion, polyethylene glycol as the heating agent, dioxide as the stabilizer, and distilled water as solvent. While for the synthesis of silver PMMA nanocomposite via in situ technique, polymethyl was used as capping agent and dimethylformamide was used as solvent. There are two steps for preparing silver PMMA nanocomposite. For the synthesis of silver nanoparticles, silver nitride was dissolved in a mixture of PET, dioxide 19, and distilled water at 80 degrees Celsius and stir with magnifying bar in order to measure the reaction. The color of the dioxide 19 solution was changed from colorless to transparent light brown upon the addition of silver nitride. This indicates the formation of preliminary silver nanoparticles due to the reduction of silver ion by dioxide 19. Then the solution was centrifuged at 50,000 rpm and washed with distilled water. While for the synthesis of silver PMMA nanocomposite, PMMA was dissolved in PMF solution. Then the pressing solution was of silver nanoparticles were added so as to obtain 6, 8, and 10% loading of silver nanoparticles in PMMA. The entire processing was carried out in the steam hood under constant stirring at 80 degrees Celsius. The mixture was further stirred for 1 hour in order to measure the reaction. The sample was heated at two temperatures, that is 100 and 120 degrees Celsius, to study the properties of silver PMMA nanocomposite at different reaction temperature and also concentration. The benefit of using PMMA is well known for nanoparticles. The first one is the availability of carboxylic functional group. The arsenide in PMMA are considered to be better suited for chemical bonding with the metal ion and high solubility of PMMA in solvent. DMF is more suitable for silver nitride reduction. The color of the composite material depends on the nature and the concentration of silver particles as well as on the synthesis condition. Similarly, as the percentage loading of silver nanoparticles in PMMA and reaction temperature increase, the color becomes more intense. This figure shows the sample of silver PMMA at 80, 100, and 120 degrees Celsius. It changed from light brown to dark reddish brown due to the different types of silver PMMA nanocomposite. For the calculation of silver PMMA nanocomposite, I will explain the results for morphology and physical studies using transmission electron microscopy, optical studies using UV spectroscopy, and thermal studies using CGA spectroscopy. For the morphology and physical study, at 18 degrees Celsius, the average particle size of silver PMMA with 10% loading of silver nanoparticles are 24 nanometers. Spherical shape and narrow particle size distribution were observed. All single PMMA nanocomposites were well bounded and separated with white layers to confirm that the presence of mercury metabolite. At 100 degrees Celsius, the average particle size of single PMMA nanocomposite is 10% loading of single nanoparticle are 50 nanometers. What distribution of single PMMA nanocomposite were observed in this sample? As the surface temperature increased up to 120 degrees Celsius, the average particle size of single PMMA nanocomposite is 10% loading of single nanoparticle are 50 nanometers. Moderate accumulation were observed in this sample. This is due to the particle size increase due to the aggregation of smaller particles resulting from dissolution and precipitation process during synthesis. Now we go to the optical studies of single PMMA nanocomposite. This figure shows the absorbance spectra of single PMMA nanocomposite at 80 degrees Celsius with 6, 8 and 10% loading of single nanoparticle in PMMA. The SPR peak are blue shifted that is moving to the lower wavelength and their full half maximum become narrow as the percentage loading of single nanoparticle in PMMA increase. This indicates the particle size decrease and become more uniform when the percentage loading of single nanoparticle in PMMA increase. This figure shows the absorbance spectra of single PMMA nanocomposite at 100 degrees Celsius with 6, 8 and 10% loading of single nanoparticles in PMMA. The SPR peak average indicates that it is moving to the larger wavelength as the percentage loading of single nanoparticles decrease. This means that the particle size at 100 degrees Celsius is bigger compared at the 80 degrees Celsius. Well, this figure shows the absorbance spectra of single PMMA nanocomposite at 120 degrees Celsius with 6, 8 and 10% loading of single nanoparticles in PMMA. The SPR peak shifted also moving to the larger wavelength as the percentage loading of single nanoparticles increase due to the larger particle size. As the temperature increase, broader SPR band were observed due to the agglomeration of the particle and also due to presence of oxide layers. The increase in maximum absorbance temperature is attributed to the more stable nanoparticle formation. This figure shows the transmission spectra of single PMMA nanocomposite for 6, 8 and 10% loading of single nanoparticles in PMMA at 80 degrees Celsius. As the percentage loading of single nanoparticles in PMMA increases, we can see that the transmission spectra decrease, which shows that single PMMA nanocomposite at higher percentage loading of single nanoparticles absorb more light due to the smaller particle size. The dip at around 430 nanometers is attributed to the dipolar resonance of single nanoparticles in interaction with PMMA. This figure shows the refractive index spectra of single PMMA nanocomposite for different percentage loading of single nanoparticles at 80, 100 and 120 degrees Celsius. The refractive index of single PMMA nanocomposite was calculated using Fresnel equation. The reflectivity of the single PMMA nanocomposite is characterized by the interference rate, which makes it possible to determine the value of refractive index to certain degree of accuracy. The interference extreme at selected Fresnel ranging from 400 to 500 nanometers is due to the plasmon resonance of single nanoparticles. The inclusion of single nanoparticles into the media with the refractive index more than 1 leads to the broadening and shifting the plasmon resonance rate to longer wavelengths. Now we go to the thermal studies of single PMMA nanocomposite. This figure shows the DEA curve of single PMMA nanocomposite at 6, 8 and 10% loading of single nanoparticle in PMMA at 80, 100 and 120 degrees Celsius. At 80 degrees Celsius, the first stage decomposition started at 223, 240 and 253 Celsius for 6, 8 and 10% loading of single nanoparticle in PMMA. It is found that single nanoparticles with 6% loading of single nanoparticles have lower decomposition temperature, however, gone much higher when the percentage loading increases up to 10% loading. Thus, it is understood the percentage loading of single nanoparticles in PMMA enhance the thermal stability of the polymer. The occurrence rate occur around 200 to 450 degrees substances which depend on the reactant temperature and also the concentration of stable nanoparticles in PMMA. This thermal stability can be ascribed to the fact that the presence of stable nanoparticles in the polymer matrix confine the motion of polymer change and serve as a reversion site for enhanced crystallization nanocomposite. Whereas the temperature increases up to 1 to 4 degrees Celsius, the incorporation of stable nanoparticles in PMMA shifted the decomposition towards higher temperature. This table concludes the thermal study of stable PMMA nanocomposite. The total weight loss percentage decreased as the percentage loading of stable nanoparticles in PMMA increased, and also the total weight loss percentage increased as the temperature increases. As the conclusion, the sample subjected to higher percentage loading of stable nanoparticles at 80 degrees Celsius were found to be the more effective and stable nanoparticles. Stable PMMA nanocomposites were successfully prepared by in situ technique with stable nanoparticles were well dispersed in the PMMA. The refractive index of stable PMMA nanocomposites showed the enhancement as the percentage loading of stable nanoparticles in PMMA increased, and the thermal analysis showed that an increase in the percentage loading of stable nanoparticles from 6 to 10% loading, there is an enhancement in the thermal stability of the PMMA.
What's the long-term effect? Would there be any segregation?
Segregation for the segregation of the center of the
part of plans to do some long-term studies of the segregation of
we are the stabilizers. The tube of the is important in this study. So for now, I use that 19 because it has a strong interaction of the property of that 19 to the structure of the nanoparticles. So we can reduce the equation of the sample. And also when you use the in this study, and will have around the stable nanoparticles. So extraction and the particles must be treatment will be decreased. Why do we choose PMMA instead of other layers of polymers? Oh, because not the use of PMMA compared to the other polymers such as PVA and PVC. Because other layers use PVA, but the stability could not translate into the long term. So this is the reason for the formulation. Yeah.
what do you think? Is that stability is an inherent property of PMMA?
Because when we get another particles in nanometer level, the property of this sample enhance mapping. So for my sample, when the size too small, for the optimum result at 80 degrees Celsius and 10% loading, I get the optimum property for optical fiber, especially in optical fiber compared to my previous research.
All right.
No more. Oh, okay. That's all.